Good morning all. Today we will be doing an experiment to plot the profile of a forced vortex as we have done in the last class with the free vortex. Unlike the free vortex formation in which no external force is applied, for forming a forced vortex, we need to apply an external force. So this can be considered as a phenomenon of rigid body rotation. So let's now rotate the vessel with the water so that a forced vortex is formed. For this, we need an apparatus, an external energy to be supplied to the vessel for rotating it. So now you can see that the vessel starts rotating. Let's all wait for a stable vortex to be formed. Now a stable vortex is formed. Similar to the free vortex experiment, now we have to plot the profile of the vortex. For that, we have the gauge needle attached to the vessel, which can be operated horizontally as well as vertically by using the pins. So let's now adjust the needle in such a way that it touches the surface of the free surface of the vortex. For the horizontal reading, you can use the horizontal scale. So record the x coordinate and the y coordinate. Similarly, the needle has to be adjusted. Adjust the needle using the horizontal and vertical scale and take at least 5 readings from along the radius of the vortex so that we get sufficient points for plotting the experimental profile. This is the tachometer for measuring the RPM of rotation. In the forced vortex experiment, all the water particles are rotating with same angular velocity. So using the tachometer, we can measure the angular velocity of rotation, and using V is equal to R omega formula, the velocity of flow at any radial point can be calculated. So this will give the theoretical profile of the vortex. So this is the tachometer, and if you press here, you will get the laser beam. Okay, and the laser beam should be directed towards the white marking in the road, which will give the RPM. So now it is recording the RPM of rotation. So with this, we have finished the experiment on plotting the profile of a forced vortex. Thank you.
Let's now discuss how to do the calculations using some sample values. As we have studied in the theoretical classes, in a free vortex, each particle moves in a circular path with the velocity inversely proportional to the radius from the center. So the tangential velocity can be expressed as q is equal to k by r, where k is a constant. So when the vortex is steady, the Bernoulli's equation can be applied. Let's assume h naught be the height of the vortex when r tends to infinity, and let h be the height at any particular radius r. Applying a Bernoulli's equation and the boundary condition at free surface pressure is equal to 0. The equation for the plotting the profile of the vortex like h is equal to h naught minus k square by r square 2g can be obtained. Using this equation, the theoretical profile of the vortex can be plotted. And we know that the velocity, tangential velocity q can be calculated from the hydraulic head h, which is obtained from the pitot tube readings. Let's now move on to the sample calculation. Let's first consider when the inlet was normal, what were the readings we got. The discharge rate at which we got a steady vortex was found to be 1000 liter per hour, and the hydraulic head from the pitot tube is 6.8 centimeter, and the pitot tube arm length, that is the radius at which we have got a hydraulic head of 6.8 centimeter, is 2.2 centimeter. So from that, the tangential velocity q is calculated as q is equal to root 2 gh. And from after obtaining q, we can calculate the constant k, and using this k, and we can calculate k square by r square 2g at every radius for which we have taken the experimental readings. So the table shows the x coordinate obtained from the experiment and the corresponding y coordinate. That means the readings taken from the measured from the needle gauges. So a plot of this x experiment versus y experiment will give us the experimental profile. Now we have to plot the theoretical profile. So the theoretical profile can be plotted using the equation h is equal to h naught minus k square by r square 2g. H naught is the height of the vortex when r tends to infinity, and it was found to be minus 12.2 centimeter. So the third column in the table is k square by r square 2g, and from that the theoretical y coordinate is calculated for all the x measured in the experiment. So a plot versus x experiment versus y theory will give the theoretical profile of the vortex when the inlet was in the normal direction. So this graph shows a comparison of the theoretical profile and the experimental profile for a free vortex flow, and we can see that there are at some differences between the theoretical and experimental profile, which could be due to the error in the P22 readings or the needle gauge readings which we have taken. Similar set of calculations should be repeated for the when the vortex was formed using the tangential. So this slide shows the sample values for a tangential inlet. So we can see that the discharge rate is less than that we have obtained for a normal inlet. That means a steady vortex is formed at a lower discharge rate when the inlet is in the tangential direction. Also, the pitot tube readings are higher than the previous ones. That means this vortex is having a higher velocity than the previous vortex. So, similar to the previous slide, we have to plot the profile of the vortex. The sample calculations methods are the same. With this, we have completed the calculations of experiment of plotting the profile of a free vortex flow. Let's now move on to the forced vortex flow. So from the theory classes, we know that the forced vortex flow can be considered as a fluid rotating as a solid body. So then the equation, Navier-Stokes equation in R component and Z component can be written as shown in the slides. And when we substitute these equations into the pressure differential, an equation where P is equal to rho omega square R square by 2 minus rho GH plus C can be obtained. Applying the boundary condition of r, at r is equal to 0, let h is equal to h naught and p is equal to p naught. And at another p in another point in the same free surface, if we apply this equation and subtract first equation and the second equation, we will get p minus p naught is equal to minus rho g h minus h naught plus rho omega square r square by 2. When these 2 points are at the free surface, we know that both p is equal to p naught. Hence, the equation h is equal to h naught plus omega square r square by 2g can be obtained. So this equation will give the theoretical profile of the forced vortex. Let's now move on to the, with the tachometer we have measured the angular velocity omega, and it was found to be 192 rpm, which is 20, which should be converted to radians per second, and here it is 20.94 radians per second. Now x reference is the x coordinate at which we have started uh, measurements, and h naught is the height of the vortex when r is equal to 0. So the first column gives the experimental reading and of the x coordinate. Subtracting the reference value from the first column, we will get the radius of the vortex at which the y coordinate is measured. Y experiment is the y value or the height of the vortex at the corresponding x. Now using omega, r and g, omega square r square by 2g can be calculated for each x coordinate. A plot of r versus y experiment will give the experimental profile, and the plot of r versus y theory will give the theoretical profile. In this case, we can see that there is a perfect matching between the theoretical and experimental profile of the forced vortex. With this, we have completed the calculations for free and forced vortex flow. Thank you.